Good evening everybody and welcome to my presentation. Today I would like to talk to you about performance characteristic of the prompt gamma neutron activation analysis system based on new deuterium neutron generator. I have divided my presentation into three main parts. First of all, I will talk about the CNSTN-DD neutron generator, operation and characteristic. And second, we will look at the performance characteristic of the BGNA system, different shielding material around the generator, measured of the neutron yield and neutron production efficiency, and generator current as a function of accelerator voltage, dose rate measurement, and finally I will tell you about the prompt gamma neutron activation analysis of the boron. For laboratory from away from research reactor could be neutron generator based solution for several neutron application. Practically, the DD neutron generator are a cost-effective, easy to operate, and practically safe alternative to another neutron source. This generator could be effectively used for research and educational purposes at university. CNSTN has created a DD neutron generator with neutron yield 510 to 9 neutron per second. We start with the characteristic of the CNSTN-DD neutron generator. This figure shows the generator around by height density of polyethylene. Our generator is based on deuterium-deuterium reaction, turnkey operation, 3-minute start-up, interchange of the target and iris, easily transportable, pulsed beam possibility, and deuterium in the target totally replaced. No radioactive tertium, but we need the height power, height voltage supply, and height power RF generator and chiller. As you can see in the section view of the generator, we have here the RF antenna, RF anion source, target, anion beam, vacuum pump, water supply for the target, and secondary electron shroud and height voltage cable. The height voltage acceleration is between 16 and 125 kV. Neutron maximum yield is 10 to 10 neutron per second. D plus fraction is more than 18% at RF power 1 kW. Maximum beam current 13 mega ampere at 4 kW, and the target used is titanium target. Neutron energy is fast, equal to 2.45 MeV, and the power equal to 3 kW. For the dimension is 16.4 centimeters for the length and 25.4 centimeters for the diameter. Let's look at the supporting system of the generator. Generator here housed by the polyethylene blocks, the turbo pump, the RF matching box, the water distribution box, and the deuterium link valve with the regulated boat of the deuterium. The RF generator of frequency 13.5 MHz of approximately 3 kW ionization the deuterium gas, forming a plasma using a Haeckel RF antenna. For the cooling, the RF supply, RF matching box, and plasma chamber using a chiller with 4 kW. For the target, we using the water chiller with 10 kW that both cools and ionization the water. The vacuum is maintained in the height voltage section by a turbo pump and routing pump, which are continuously operating. As you can see, the major electronic components are stacked in electronic rack. The turbo pump, control, and various vacuum, water conductivity, and pressure gauges are at the top. At the bottom of the rack there is a high voltage power supply flooded by the RF generator. During the installation of the neutron generator, we encountered a lot of the problem. The first was with the high voltage column, which behind construction for 2 times. This caused water and fluorinate mixed up, and this has an effect on creating a vacuum. In the first time, we kept the resin and we changed only the cooling tubes that present in 2 first figures. This solution doesn't work. In the second time, we change all the form of the column that's present in these 2 figures. The second problem is the 8 voltage cable. We see in the last figures the effect of the spark on the cable. Now I would like to move into the second part, performance characteristic of the CNSTN-DD neutron generator. This figure shows you neutron generator and the two detectors from neutron yield measurement as a function of accelerator voltage. The two detectors was placed at 1 meter from the source, exactly from the target, and the yield was measured at two locations, 19 degrees and 100 degrees relative to the anion beam. The result of the neutron yield as a function of accelerator voltage for two different measurement angle and two different plasma power are shown in this figure. As you can see, the increases in the yield for 118 degrees direction is approximately 1.7 times. The neutron flux increases approximately linearly with the accelerator voltage, the maximum production of monoenergetic neutron with neutron yield equal of 4.5 10 to 9 neutron per second. To be illustrated this, we have plotted the experimental and theoretical neutron production efficiency. We also measure the anion current as a function of accelerator voltage and plasma energy. The result is shown in the two figures. We have here pass-through value that varies with RF power. The anion increases with the accelerator voltage. The 8 neutron output was archived with accelerator voltage of 125 kilovolts and RF input power equal to 2.5 kilowatts. It's very well known that the shielding of the neutron is a complicated problem due to the fact that the both neutron-photon interaction with the material need to be considered. Therefore, for surface introduced in the neutron and photon dose rate, the generator has been shielded by high-density polyethylene, borated polyethylene, and the lead. We present here in these two figures our shielding around the generator. For example, in the west we used 13 centimeters of high-density polyethylene and 5 centimeters of borated polyethylene and 5 centimeters of the lead. Also, neutron yields are one of the most important aspects determining the performance of the neutron generator. For this reason, we measure it at the sample position in the BGNA system. For example, in position number 1, we have the neutron yield equal to 1.8 10 to 8 neutron per second, and in the position number 3, equal to 1.67 10 to 7 neutron per second. The experimental measurement and the theoretical estimation of the neutron yield in agreement with relative error less than 10%. Now I will focus on the neutron and gamma dose measurement location inside the activation room. We present in these two figures the neutron generator, different shielding material, and neutron detector. For example, position 1A is in contact with the lead and 2A is in 100 centimeters from the lead. The dose rate inside the activation room during operation and comparing them with Monte Carlo calculation are shown in this table. The neutron and gamma dose rates is in the generator where the prompt gamma activation analysis system will be installed at 100 centimeters are approximately equal to 58 microsievert per hour. In this case, the annual limit of operating hours for the operator will be 345 hours corresponding to annual limit of 18 millisievert. Now I will talk about one of the problems in the neutron generator shielding. In the west of generator, the neutron dose rate at 1 meter detector position in the graph from the generator is equal to 126 millisievert per hour. With the generator equipment, it's difficult to construct a good shielding. I think in the future, I will use the paraffin in this site. Let's look at the dose rate in the neutron activation laboratory outside the activation room. We present in this figure the neutron activation analysis laboratory. For example, in the control room next to the activation room, the dose rate is 9 microsievert per hour for the neutron and 0.35 microsievert per hour for the gamma. This room is the controlled area. In this case, the annual number of operating hours for the operator should be lower than 2 pounds hour. Now, I would like to move on the prompt gamma neutron activation analysis of the boron. We present the BGNA experimental step. We have here the generator surrounded by the polyethylene moderator and the lead shielding. We use it 4 inch of the polyethylene to thermalize 2.45 MeV of the neutron. 4 inch of the lead separated the polyethylene from the sample chamber and the detector to chill the detector from the gamma. 2 inch of the lead chilled the detector. The HPG detector measured the gamma ray energy spectra. Calibration of the HPG detector with cobalt, cesium, and sodium selected source. Now I would like to look on sample preparation. 2 steps of the samples was prepared, one in silicon matrix, the other in silicon dioxide. The sample composition is present in this table, and the first figure presents 3 boron sample prepared in silicon and 1 block without boron, and the second figure presents the boron samples in silicon dioxide matrix with Rowley to demonstrate the scale. This graph shows you typical energy spectra measured with the HPG detector. We have the boron sample in blue and the background in red. Boron is detected throughout the 470 kV gamma ray emitted in the boron-lithium reaction. There are numbers of peaks due to neutron interaction with germanium crystal. However, these peaks do not interfere with the boron peak region. As qualitative comparison, this figure demonstrated energy spectra of the boron sample taken with an eye detector. The eye detector was warped in cadmium food to reduce sodium and iodine neutron capture reaction. Subtract very nicely to yield boron peak. Small shifts in the sample and active background energy spectra due to the variation of the height voltage supply can make the background subtraction more complex. The HPGE or the semiconductor detector is best suitable for qualitative and quantitative analysis. I would like now to move on the neutron and energy distribution at the sample position. This figure shows us a typical energy spectra showing the various components used to distribute the neutron energy region. The neutron energy distribution was then taken at the outer surface of the lead slab. Thermal and epithermal neutron account for about 45% of moderator neutron, and intermediate and fast neutron account for approximately 47% of the distribution. The neutron flux from the DD neutron generator with output 510 to 7 neutron per second at the sample position is approximately 3.15 10 to 3. Neutron energy category and her percentage of boron-lithium reaction are present in this table. The percentage of the interaction in the boron sample due to the neutron thermal neutron is approximately 31.3%, and that due to the fast neutron is 0.01%. Epithermal interaction accounted for 67.69% for the total of boron-lithium interaction. The fractions were derived from the neutron energy distribution along with boron-lithium cross-section found in the NDF B7.1 database. Now, I will talk about the HPG neutron damage. We present in this table the percentage of the neutron interaction as a function of the neutron energy category in the germanium detector. We have 32.37% of the total neutron interaction in germanium crystal are due to the elastic scattering, intermediate and fast neutron. In addition, 30% of neutron and gamma reaction from thermal and epithermal neutron. Now we show in the first figure the plot of silicon and silicon oxide datasets fit by the single cover. The silicon dataset has been normalized to the silicon oxide dataset to count for different in solid angle to the sample position relative to the detector. And the second picture presents the simulated count rates recalculated with the neutron energy distribution calculated with the MCMP along with the cross-section for boron-lithium reaction for the NDF7 database. The cover in the first figure is also highly dependent on the sample geometry and its orientation to the neutron flags. The values plotted on axis can become very complicated for irregular shaped samples. And for the second picture, the calculation is 21.82% lower than the NDF databases, implying that the neutron energy spectra calculated with the MCMP is a better harder than that of ours. The comparison of the net spectra of 0.0 gram and 0.05 gram of boron measurement present in this figure. This comparison demonstrating that 0.01 gram measurement is luckily below the detection limit, whereas the 0.05 gram measurement is over the detection limit. Thank you for attention.